Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Ashley Davis with us today. Hello, Ashley.
Good morning, Frank.
Good morning on this June 17th of 2024 as we record this. And Ashley, what's your geolocation? Where are you at?
I'm at the Jet Propulsion Laboratory, California Institute of Technology in Pasadena, California. And it's a beautiful
Very cool. And it's June, so are we having June gloom in Pasadena?
We're having fire season. It started.
Fire season. It's already started. Oh no. So I'm in Phoenix, and we are definitely into our triple-digit Fahrenheit temperatures.
I'm sure.
Indeed. And there's no fires because every day is just fire in the afternoon. It's wild. Boy, you sure got a lot of preprints and books over your right shoulder there. That's pretty awesome. Look at all that.
Oh yeah. Yeah, actually, this side aren't books. This is that top shelf, all my notebooks.
Very cool.
I shifted years ago to electronic format.
But
so my journals, all my projects are electronic, but this is the analog stuff from prior years. Still very useful, very good things to have. Anyone out there, keep your notes, keep them safe.
Very good. Awesome. Cool. Oh, okay. And Ashley, what do you like to do? What do you like to do in those notebooks? What do you like to do for research?
I study volcanic eruptions on Earth and on Io and elsewhere throughout the solar system. I seek, through the use of remote sensing data and fieldwork whenever possible, to understand how and why volcanoes erupt and how they present to remote sensing, so that I can use what's happening down here to understand what's happening out there, and what's happening out there to understand what's happened down here.
Very cool. It's funny how that works in a big circle like that. It's very cool. And that is going to bring us to this very awesome Planetary Science Journal article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
It's a right riveting read.
New global map of Eo's volcanic thermal emission and discovery of hemispherical dichotomies. And Ashley, take us away.
Oh, well, Frank, this was the result of a lot of work by myself and especially my co-authors, Jason Perry, who is at the University of Arizona, Dave Williams, and Dave Nelson. Go home team.
Arizona State University.
Right. Dave Williams and Dave Nelson at ASU, and Glenn Vida, who for many years was at JPL, and thinks he's retired, but when he thinks he's out, I just drag him back in.
Pull him back in.
And Glenn was the leader of a lot of the work that this paper is based on. So I'm very happy to have him working on this with us.
Cool.
So
good
yeah.
So get into it.
Let's get into it, indeed. So what we've been doing is looking at the distribution of volcanic activity on Io as a proxy for internal heating. So Io is this large moon of Jupiter. It is caught in a gravitational resonance with two other Galilean satellites, Europa and Ganymede.
Yes.
And so this leads to a lot of enhanced tidal heating.
Yes.
This heating manifests as luminous, powerful volcanic activity at Io's surface.
Cool. So
one of the things we don't know is exactly where this heating is taking place within Io. And so for literally decades, researchers have been looking at the distribution of volcanic activity, both the number of hotspots and the actual power emitted per hotspot, as a proxy for volcanic. Well, obviously that's a manifestation of volcanic advection, but it's being used as a proxy for internal heating.
Nice.
Because we don't have this is just a surface manifestation which we can actually observe and chart. And ever since Voyager, back in 1979. We've been using multiple assets and every opportunity we can to try and understand more about Io's volcanic activity and the distribution of volcanic activity. And surprisingly, you know, a lot of people have concentrated on the number of hotspots that are there on Io, and to me, that's not particularly interesting or informative. I'm much more interested in the amount of energy that's coming out from each hotspot as a better manifestation, a better proxy for you know, the volcanism that's taking place.
Right. Gives you a sense of the energy total.
Yeah, yeah, it's the energy output that's the important thing. It's not necessarily how many hotspots there are.
You could have one big one,
and yeah, so back in 2015, we published the first map of where activity was taking place on Io in terms of thermal emission from its volcanic centers. And this was always sort of limited because we never had a good look at what was happening in Io's polar regions with instruments that were sensitive to thermal emission from ongoing volcanic activity. All of this changed when the Juno spacecraft went into polar orbit around Jupiter.
Yes.
And started making passes of Io and looking at what was happening at Io's poles. And this was something that had never been seen before. Cool. With short wavelength infrared images. There's a short wavelength. It's an image. There's an instrument called GIRAM on the Juno spacecraft, and both the project and the GIRAM and the JunoCam teams have been, you know, carrying out heroic efforts to keep everything going and getting these incredible data sets of Io's poles. So what we did was, and this is based on, we first, you know, looked at the distribution of 4.8 micron spectral radiance at Io's poles, and published that in a paper in competition at around about the end of the year, 2023, in Nature Astronomy. But then, you know, we were already working on taking the estimates of thermal emission on from the GIRAM data, informed with information from the JunoCam imager, to start filling in the gaps in coverage, not just longitudinally, but latitudinally. And this paper takes all of the detections that we've made with Juno and added them to all the detections made from previous spacecraft and from ground-based telescopes over the last decades, to come up with the first truly global distribution of hotspots and power emission and the distribution of power emission. And that's what's described in this paper. We find some very, very interesting stuff.
Indeed.
So I think we really covered sort of the observations of volcanic activity. So if we scroll down to the first figure, this is figure 1.
Beautiful.
This is the distribution of hotspots. It's a more-wide projection. The center is 180 degrees west, which is the anti-Jovian point. This is the point on the far side of Io. Io's phase logs, of course. And we see, you know, in total, 343 individual volcanic centers. Some of them, it's difficult to tell whether it's, you know, a single volcano or whether it's two volcanoes close together. But again, we're interested in how much energy is coming out of these volcanoes, rather than their precise, you know, sort of number in a given area. It's the power output that's the important thing. So we see, you know, a broad range of thermal emissions, just reflecting, you know, huge differences in scale of volcanic activity, and the volumes of material can be inferred from that. But you know, this paper is basically focused just on the energy output. Cool. So yeah, so so if you scroll down to the second panel here.
Let me ask a trivia question.
Of course, yeah.
On these yellow ones. So those are the big power ones.
Those are the biggest ones. Yeah, we're talking about power here, you know, in excess of we're talking about terawatts of energy now.
Yes,
it's absolutely astounding that we see, you know, hotspots on Io that emit this amount of energy.
And of the yellow,
especially when compared with terrestrial equivalents.
Oh yeah, yeah.
The scale of volcanic activity in Io is just so much larger than it is on contemporary Earth. So
just a trivia question then: of the yellow ones, which one puts out the most power? What's
Loki Patera? Persistently, if you go over to about 310 degrees west, over on the left-hand side, you see Loki Patera is highlighted here.
Okay.
Truly remarkable volcano. It's Io's most powerful persistent volcano. We get eruptions on Io which can generate tens of terawatts,
Mhm.
which always raises the eyebrows of any
Good.
terrestrial volcanologist when you say that. But Loki Patera consistently outputs about 10 terawatts. It drops down to a few terawatts. It can go up to 15, 16 terawatts as resurfacing of the Patera floor takes place.
Cool.
That's the average is about 9.6 terawatts, which is just phenomenal.
Yeah.
It's the equivalent. It's the equivalent of about 100 cubic kilometers of lava moving through the system and losing heat every year. And
Wow.
it's done this ever since it was discovered as an active volcanic center in 1979. It is
Yes.
phenomenal volcanological feature which we're still trying to understand. It's probably sort of like a mantle hotspot to supplying this vast amount of magma on a yearly basis.
Beautiful.
So that's Loki. That's Loki Patera.
Beautiful. Okay. Apple one. Sorry about the slight interruption there. Okay.
So
That's
roll down to figure 2.
the ortho.
This shows the North Pole on the left and the South Pole on the right.
Yes.
And we filled in all of these new hotspots that haven't been seen before because we've never really had a good look. And what we found from the paper that was published in Nature Astronomy, first of all, was that there wasn't really a great number of additional hotspots in the polar regions.
Okay.
Compared with lower latitudes. And this was a big departure from what was thought before Juno arrived at Jupiter. Because from our sort of equatorial perspective, which is what we've seen from Voyager, to some extent, actually Voyager 1 went past the South Pole. It didn't have a short wavelength thermal imager on board. So most of the observations we have are from Galileo, which was mostly in the equatorial plane, New Horizons, mostly in the equatorial plane, from Cassini, in the equatorial plane, and from ground-based telescopes and Hubble in the equatorial plane. And it was thought from the observations over the decades that Io's polar volcanoes were fewer, but more powerful and perhaps more transient than what we see at lower latitudes. And we found something that was very different to that. We find that the number of volcanoes there is about the same. We just didn't have a good look at them. And I think there was just some observational bias that was put into place in the obviously there was no way of knowing until we took a look at the poles, and that the reason that we were seeing these powerful but infrequent eruptions in polar regions is because of just viewing geometry. If you have something which is actually throwing up large lava fountains or something, you'll see them. But if something is in a depression and is just chugging away at a low level, you won't. So that was the first big surprise. I have to say that there's a difference in spatial resolution between what we see at the north and what we see at the south, because most of the observations with Juno have been of the northern hemisphere, not so much of the South Pole, although that has been corrected. And I don't think that's really all that important, because we're interested not so much in the number of hotspots, but in how much energy is coming out. And even in the low spatial resolution observations, we see energy coming from hotspots in the South Pole. And if there are smaller hotspots there, well, they're not putting out very much energy. And so it's not going to skew the results at all. So things are looking good. But this is the combined data set. If we could scroll back up to 1, this is the full data set of the 343 active volcanic centers that we see on Io, from combining the Juno data with all of the data that have been obtained in the past. So if we scroll back down,
very cool. Okay.
Past figure 2.
Okay. Here's our hotspot detections.
There's the paper goes into what we had before, the changes that we've made to the previous 2006-2015 analysis, which was updated. We had to make some assumptions back then, which we can now correct because we have better data to confirm what we found,
Cool.
to refine some of the numbers that we used in 2015. And scrolling down again, we talk about in the paper, we talk about the previous work that's been done. We talk about polar volcanoes, as I've just described. And if you scroll down to figure 3, which is just down here.
Oh, here we go. Power.
If you just go up a little bit. Yes, and this was from the Vida et al. 2012 and 2015 papers. Which and then the Davies et al. 2015 heat flow map that was published in Icarus, which shows in sort of broad bits of 30 degrees of longitude where power appears, and you see that there are peaks and there are troughs. Round about 0 to 45 degrees west, there was relatively poor coverage by Galileo. And so we'll get to that in a minute. And the red arrows here show where for one of the heating models, the asthenospheric shallow tidal heating model, where you would expect to see peaks in thermal emission. So it's not a great fit, basically. If you scroll down again, if we can exit from this figure and scroll down, we go into how we calculate thermal emission. It's pretty straightforward. There's nothing different about that. If you scroll up to figure 2, sorry, equation 2 is right there. It is. Yeah. In some cases, we have data where we only have one wavelength. And if you have one wavelength of data and nothing else, you don't understand. You don't know what the total power emission is because you've only got one wavelength.
Right.
So what we did was we looked at an analysis that we published, that Glenn Vida and I published in 2023 in JVGR. No, it was the JGR Planets, where we looked at hundreds of hotspot spectra obtained by the Galileo NIMS instrument, another infrared imager, throughout the Galileo mission. And we came up with this sort of empirical relationship, which kind of relates how much total power you get out of a hotspot just from 4.8 micron wavelength. And this can vary by an order of magnitude up and an order of magnitude down. It's a real sort of rule of thumb, but it's better than nothing. It gives us something that is based in a previous analysis. And as soon as we get extra data, we can then just refine those numbers. And this is just a handful of hotspots where we just had a 4.8 micron radiance. And there are various ways of dealing with that. And we're using this for the time being. But if we can get something like an emitting area from, say, a JUNOCAM observation, we can then take the area, we can take the spectral radiance of 4.8 microns, and we can actually come up with what the effective temperature is. And if you have the temperature and you have the area, then we can work out what total power is. And we can just refine that small number of hotspots. Something else I need to talk about, of course, is what we call a polar cap. We picked 60 degrees as a polar cap definition because the models of interior heating predict different amounts of energy coming out of the poles and coming out at lower latitudes. So if you have, say, deep mantle heating, you have a dearth of thermal emission at lower latitudes, but a lot of thermal emission, a lot of heat flow at Io's poles. And if you have an asthenospheric heating, which is in the shallow asthenosphere, and say possibly a global magma ocean, which might be global or partial magma ocean, that gives us more thermal emission at lower latitudes and less thermal emission at the poles. So if you want to compare the poles at low latitudes, you have to come up with a definition of where the polar discriminator is. And we picked 60 degrees for a number of reasons. The first reason is this is where you have the biggest difference in the radially integrated heat flow models that have been used for decades to try and understand the patterns of heat flow on Io. And secondly, previous users have used 60 degrees. as a discriminator, which means we can compare our results with previous analyses.
Good, good.
Okay, so shifting down again to shifting down, yeah, I mean, hotspot detections and sources and data processing is all it's all pretty dry stuff. But figure 4 is actually, I think, one of the more important figures, because it shows with the black dots where hotspots have been discovered in Juno data that weren't previously identified by any other asset.
Aha, cool.
So the white dots show where we've seen these are the hotspots that we used in the Davies. Thank you for putting your circle around it. Yeah, yep. That was the 2015 heat flow map.
Okay.
And the black dots are where we've added in to that data set, which was 250 hotspots, where we've added in subsequent detections after 2015. So this includes data obtained from ground-based telescopes using adaptive optics, such as Keck and Gemini, the Large Binocular Telescope array in Arizona, the Large Binocular Telescope Observatory in Arizona, and of course Juno. So
beautiful.
There are a couple of colored hotspots here, and what's happened here is that these were previously detected hotspots, but then we find that they're either very transient, so we use an average, and position might have changed because a lava flow might have moved, and so there's a different location of the hotspot, or we have better resolution of the hotspot where we find different locations. So there's a bit of wiggle room in hotspot detection locations there, but mostly it's because of the lower spatial resolution of the previous observations, and now we have better refinement with Juno data.
Okay. Okay.
So you'll see that between between 0 and 60 degrees west, there's this cluster of new hotspots that Juno has detected. And this was an area that was poorly covered by Galileo, just because it's there close on the subjovian hemisphere, close to the subjovian point.
Right.
Okay, so scrolling down, please, if we could go back to
hotspot entry.
Okay, we have some updated entries, and then there's a section on how we process the GIRAM data. It's a lovely instrument, but there are some quirks that you have to be aware of when processing it, just like any piece of hardware. We have a load of hotspots where things have been updated. Now, what we did then was we did carry out some analysis of hotspot numbers and total power, just to see if there were, where the discrepancies were. And we do find some hemispherical differences between, and this is this is very broad, right? This is looking to see if there's anything happening. Subjovian, antijovian is interesting, because on the subjovian hemisphere, we have actually fewer hotspots. Difficult to tell, 163 to 180. It's not a huge difference. It's quite a big difference in power output.
Power, though, yeah,
quite a significant difference in power. Otherwise, we see that the leading and trailing, northern, southern, and the average, there's not a lot of difference in the number of hotspots on a hemispherical basis. But especially the subjovian, antijovian hemispheres start to get us thinking about, well, why is this? And we've seen what happens with a phase lock world and volcanism, just looking at the moon, where we have a lot of volcanic activity on the Earth-facing side and less on the other side. So one of the things that we're looking at.
Cool. Very nice.
If you scroll down a little bit further.
We get results, global heat flows,
longitudinal longitudinal distribution. Yeah, if we go down to figure 5, we see that we compare here our results from this analysis, which is the line with the diamonds.
Yes.
And we compare it with the 2016 map and another map that was produced by Catherine de Clear and Imke de Pater from ground-based telescope data using Keck, using hundreds and hundreds of Keck observations of Io, which was sensitive to the mid to large size eruptions on Io. And the first thing was, when Catherine and Imke published that, it was the closeness of the distribution with the Vida et al. Data, which was very gratifying. And what we find is that things have changed a bit, but not changed a lot. Some hotspots have actually dropped in intensity, others have increased. And basically, there isn't a huge lot of difference in the longitudinal distribution over multiple decades, which is kind of what you expect. I mean, volcanoes come, volcanoes go. Some erupt, they stop, they go. Sometimes there's a big eruption, sometimes there's a little one. Yeah. So, but the interesting thing is going down to the next figure, where we look at the latitudinal distribution of energy.
Ooh, I can already tell what's coming.
Let's go down to this, and what we find, and this analysis of total thermal emission, which follows on from the 4.8 micron thermal emission map just from Juno data that was in the Nature Astronomy paper, is that there are some you see a lot of energy coming out at low latitudes and at high latitudes. You see that there's this big difference between what we see at the North Pole and what we see at the South Pole.
Yes.
And basically, when you look at the averages of hotspot thermal emission and the average values in these different locations, we come to some very sort of basic findings, which is energy from Io's polar regions is only half that on a per volcano basis. It's only half that is from it's only half that at lower latitudes. So the volcanoes at lower latitudes are outputting twice as much energy on average than they do at poles.
Yes.
And the North Pole, is outputting twice as much energy
as the South
per hotspot than from the volcanoes in the South.
And
we don't know why. All of the models that are basically your tidal heating and heat flow models are linearly integrated and are based on variability in longitudinal. You see these longitudinal variations, but there's north-south symmetry in these models. But what we find is that volcanic activity is decidedly asymmetrical. Now, what can cause that? We don't know yet. It might be, I might be getting ahead of myself. Let's keep going. Let's keep going down. So we find these differences in volcanic activity at the poles from lower latitudes. And if we scroll down, we talk about that here. The
correlation with heat model,
polar comparisons. We do a comparison. We correlate. First thing we do is we looked at the distributions of hotspots. We looked at the hotspot density. We looked at how many hotspots there were per unit area. And we find that there's not a huge difference across Io, but there's a small difference between the number of hotspots per million square kilometers at the South Polar Cap and the North Polar Cap. And they're slightly lower. Both of those are slightly lower than what we see at lower latitudes. Whether or not now, we have this huge thermal emission amount from Loki Patera. So we did the calculations a number of ways. We included Loki, and we excluded it as an outlier, and we got the same results. And for our 60-degree cap, we looked at the 60-degree cap. We thought, how robust is this 60-degree cap? So we did the same analysis with 55 degrees and with 65 degrees. There was a bit of wiggle room just to see if there was a dependence on where we chose that cap.
Yeah, magic
got the
number.
same results. We got the same results. There were differences in the numbers, but the overall conclusions were the same.
Good. So to that
So
magic.
the second column is where we get some interesting dichotomies in terms of, this is just hotspot total thermal emission. And okay, there's more hotspots in the south, so we see more hotspots from, sorry, there's more hotspots at lower latitudes, so we see more thermal emission because it's just more of them.
Right.
But it's the mean hotspot thermal emission that's the interesting thing.
Yeah.
You see, at lower latitudes, we have 150 to 180, depending on whether you include Loki or not. Just for the record, I believe we include Loki in all our calculations. Okay. Because just because it's different doesn't mean it shouldn't.
Yeah, it's there.
But we did it both ways, and we got the same results, right? So, but yeah, I'm in favor of keeping Loki in the family.
Absolutely.
And you see the differences between what's happening at lower latitudes and what's happening in the north, which is about a third, and less than half, about half, roughly. 180.
Oh, wow.
Yeah, and what's happening in the south, where it's a lot less. And then skipping across to the hotspot power density. And this is, again, this is the amount of energy coming out per unit area. We see these big differences between what's happening at low latitudes, and what's happening at the poles, and what's happening between the North Pole and the South Pole.
Okay, now I get your half.
Absolutely fascinating. Yeah. So you see, 1263, 1531, low latitudes, only less than 700 at the north, and 300
half of that again. Yep. Wow. That's
so. Yeah, and then the global numbers are at the bottom. You can see that globally, there's a big difference between the global numbers and the polar numbers. So scrolling down a bit further, please. Okay. This is basically again more wide projection showing the distribution of hotspots. Nice picture. We are still filling in gaps. We're still finding new hotspots on Io from Galileo data, but I think that what we have at the moment is robust enough because we've seen all the big ones. All the big hotspots have been accounted for in terms of their average thermal emission. There might be some variability. Hotspots come, hotspots go, but I think that what we have here is a pretty robust data set showing the distribution of where the power is coming out of Io.
And just to be clear, these three are models. That's the background.
Yes, yeah, these are the models which have been developed over the years for deep mantle heating, asthenospheric heating, and more recently the magma ocean model. Right. And it's almost certain that there's a partition and that there's a mixture of asthenospheric, say mostly asthenospheric, and some deep mantle heating on Io. But you can't just take some of the asthenospheric heating and some of the deep mantle heating and smash it together. It's more complicated than that. The magma ocean model also, has a shift in longitudinal thermal output from the asthenospheric model. Yeah. But now, more modeling has to be done. And luckily, we have people working on this very sophisticated model, 3D models of internal convection, internal heating.
And hopefully that takes.
And so that's one of the avenues that we're pursuing now. Yeah. If we leave this and scroll down a bit further.
Okay, one question.
Yes, of course.
So first of all, I just want to reiterate the point you made earlier. All the theoretical models have a great deal of symmetry to them. Yeah. Right. And that's not what's there. And what is the one down here that has no anything at 180 West?
I'm sorry. What
down here on the lower right?
Oh, that's just that's the I beg your pardon. That's the just for reference sake, this is the USGS Io Global Mosaic, which was produced from both Voyager, the best Voyager and the best Galileo camera data.
Good. Okay. Good. I'm with you. Okay. Let's go down.
So so we correlated the distributions of both hotspots and power output to the actual heat flow models. And we didn't get great results. And this was not a surprise because people have been trying to do this for a long time, and they've come up with some very innovative and very interesting ways of coming up with, you know, different harmonics in the model, and different interpretations of anyway. We didn't get great correlations. Well, one thing that we did find is that the correlations with the deep mantle model were there's a strong anti-correlation. We get better results with the asthenospheric heating model and the magma ocean model, which are positive but not great positive. But the deep mantle model, you know, is a very poor fit, which is kind of what we knew already, but now we've quantified it. So from a much more complete data set.
Cool.
So
I'm with you. I'm with you. Okay.
So so in terms of what we do next, so basically just here we have our conclusions on the right here. The hotspot density does not vary greatly between polar regions and lower latitudes.
Yes.
Polar regions emit about a third of the energy seen at lower latitudes. The North Pole alone emits less energy, about 44% less energy per unit area than what we see at lower latitudes, and that's below 60 degrees on lower latitude analysis. And then there's this strange business of the North Polar region emitting twice as much energy as we see from the south.
Weird.
Which is emitting only 1/5 of the energy per unit area than what is seen at lower latitudes.
Mysteries.
Yeah, so you know, we don't know what's going on here, but this is why it's so exciting. You know, this is the discovery that we made. How do we figure it out? Well, we're looking at the geology. We're looking at geomorphology. We're looking at the geology to see if there's some geological manifestation, that perhaps difference in lithospheric composition or thickness, which manifests as in the surface expression of the geology. But it might be that we have to wait for a dedicated IO mission. You know, in full disclosure here, you know, I was a co-investigator on the IO Volcano Observer mission, which was, you know, PI'd by Alfred McEwen at the University of Arizona, and which wasn't selected in the last discovery round. But you know, this would be a mission that would very carefully measure IO's shape, carefully map out the background heat flow. Now, okay, the caveat here is that we've been using volcanoes as a proxy. Internal heat. And the volcanoes cover 2% of Io's surface, and we don't know what's happening in terms of heat flow from the other 98%. So we need to go back and we need to measure that. Instrumentation designed to do this on Io, designed to look at Io's high temperature volcanoes and to accurately measure Io's shape. So we're hoping that Juno, combining Juno data with Galileo data, we might be able to come up with some constraints on the tidal love number or other orbital parameters of Io that would give us better insight into Io's interior. We don't even know how big Io's core is, you know, and that's a huge factor. So there's lots more we can do. There are new assets coming online to help us monitor active volcanism on Io. There's a paper published just a week ago in GRL, which I encourage people to take a look at, using an imager called SHARC-Viz. It's on the Large Binocular Telescope, and it obtained data of Io, images of Io at about 60 to 80 kilometers per pixel, which is absolutely astonishing at visible wavelengths from Earth. It's equivalent to a lot of the data that have been obtained by spacecraft in the Jovian system. And plus we have the JUICE spacecraft, ESA's JUICE spacecraft, on the way to the Jovian system. And Europa Clipper is due to launch in October. And at the end of the decade, you know, both spacecraft will be in the Jovian system, and there will be opportunities to observe Io. But again, in the equatorial plane. So This is why Juno is so important. And Juno is still continuing to send back data of IO. Slowly and surely, it's being processed and released on the PDS.
Cool.
And we're heavily engaged in analyzing that. So yeah, it's a great time to be engaged in IO science.
Very nice. Very nice. And one more down here.
Yes. Now, we dedicated this paper to Dennis Matson. Dennis was the Cassini project scientist, and he was my mentor, and he was my colleague, and he was my friend. And I came out to JPL in 1994, and as Dennis's postdoc, I was a shared postdoc. Him and Torrance Johnson, he was the Galileo project scientist, and he was one of the very first people to calculate what IO's thermal emission was and what the volcanic thermal emission was in IO. And we worked together on IO stuff for over 25 years, right up until the end. And so we dedicated this paper to him.
Beautiful, beautiful, very nice. Ashley, I want to thank you so much for walking us through your very awesome PSJ article.
Thank you for the invitation to do so. And it was an absolute pleasure. It was a lot of fun to do that.
Sure. And you covered a little bit of where the future's going. And I just wanted to ask a few more questions along those lines on a happy future now. So you mentioned, so we had the basically we had the luminosity that was tagged to one 4.8 micron feature. So are any of the missions that are going attempting to do it at other wavelengths so that we can get a better handle on?
Oh yeah,
spectrum,
I mean Juno has the Juno GIRAM imager, the Jovian infrared auroral mapper, designed to look at Jupiter, but very useful for looking at IO. Capable of it has two bands in the imaging mode, 3.5 and 4.8 microns, and you can do an awful lot with that. And we are doing an awful lot with that. Others are doing an awful lot with that, which is great. There's a spectral mode which actually has hundreds of spectra between 2 and 5 microns. It's a tricky data set to use, and we haven't really utilized it in its fullest extent yet. JWST is taking some fabulous spectra, relatively low spatial resolution, but extraordinarily high spectral resolution.
Cool.
And so, you know, we're working with some of the folks on the data that JWST has been getting. And what we've been finding is that when you combine the data from different assets, you get a much, much better picture as to what's going on. Cool. So these data aren't being analyzed in isolation. In isolation, it's the bringing together of different data sets that really helps us understand really what's going on with the volcanoes, and that's a way of getting into what's happening in the Io's interior.
Very cool. Very cool. Well, I really look forward to seeing this field develop over the next.
Yeah, I'd like to show you after this is over. I'd like to show you the shark image, because it's worth a shout. It's worth a shout out.
Good. Go check it, people. Very good. Ashley, thank you so much. And that will do, everyone. And I hope this made your Planetary Science Day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you very much, and goodbye.